Hey, what's going on YouTube? Welcome to the next installment in our series building a render engine in C++. Last tutorial we created the framework for a shader system, but without today's code there's not much we can actually do with it. Today we're going to write the code to handle the fragment shader, which allows us to do lighting effects, texture mapping, and much more. Once again, I'll recommend you watch the precursor video before this one, just to make sure you have an understanding of the math. With that out of the way, let's jump right into the code. Alright, so starting off, we're going to want to jump into basic shader.h, and here we're going to implement our basic fragment shader. So just go ahead and create a class basic fragment shader and end it with a semicolon. Also inherit publicly from fragment shader. And we're going to need to add our constructor. And that's just going to take in no arguments, but it's pretty simple stuff because you just call the base class constructor with 1,000 uniform locations. So next, let's just implement the virtual methods init shader, prepare, and execute. And let's just put all those on their own little lines, and then our virtual void or char execute just takes in a dataless pointer attribute and a vector4 reference for the output. Let's just put the body in the H file because I'm lazy. We can return a period for now. Okay, so into main.cpp we can actually use this fragment shader instead of the base fragment shader. So we'll just cast that to a fragment shader pointer and delete the arguments. Make sure that you use public members for this, because it won't work if they're private. Okay, so now let's go into our rasterizer.h, where I'd like to start implementing the using the shader. The first thing we want to do is in our render triangle function. Notice how that's taking in vector 2s. If we change that to vector 4s, we'll get all the information into the rasterized triangle function, which the fragment shader is going to need, because it needs to work with depth of the variables. And we also need a shader program reference and a dataless pointer attributes. Now, the way this works is we're going to have a each vertex of the triangle is going to output a single dataless pointer, and that's going to include all the data that needs to be passed to the fragment shader. And what the shader program will do, or the rasterizer, it's going to linearly interpolate using barycentric interpolation between each of those values, and it's going to know, and it's going to pass them the consolidated interpolated list to the fragment shader, which it's going to use to do its calculations. Alright, so now let's open up our rasterizer.cpp and scroll down to rasterize triangle, and let's add in a shader program reference shader and add in the dataless pointer attribute pass, or pass attributes. And now we need to change all of these vectors to vector 4s. So once that's done, the error should go away. Alright, perfect, and remember they're all being turned to vector 2s with this calculation, so don't worry about too much past that. So now in rasterize triangle we can get rid of our current call to that, but we do need to call rasterize triangle with v1, v2, and v3. And then of course the shader program and the pass attributes, which we'll create in a second. So go ahead and delete that bottom thing. So now let's go to the top and create our dataless pointer for pass attributes. And we can set this equal to something, but we'll implement the method first. Go into shaderprogram.h and we'll create the dataless pointer pass buffers. And this is just the data that's going to be passed, but we're going to have a double array because there's going to be one for each vertex. And we'll call that size max vertex pass buffers. There's going to be one for each vertex as well as one for the actual consolidated output. So define max pass buffers and set that to 4. So now let's add in the destructor and actually delete these pass buffers. So for I equals 0, I is less than the max vertex buffers pass and I++. Go ahead and delete pass buffers sub I, and then at the end delete array pass buffers. Now we can just copy that whole loop because we're going to need to implement the, we'll initialize them. So we do pass buffers sub I is equal to new data list vs.get output count. And this is going to be a variable or a function that we set in the vertex shader that's going to just determine how many variables that are expected to be passed to the output shader or to the fragment shader. So we can actually put that into an argument into the vertex shader as max pass count. And let's just set it up as a private member and call it int max pass count. And then, of course, initialize it in the constructor with the initialization list. And now we can implement that function get max output count, or get output count, return max pass count. So let's change the data list pointer input to just the data list pointer for the attributes out. And once again, change it in the fragment shader.h or basic vertex shader.h. And in the basic shader, we can give it a pass count of 1,000. It's just the max, because it doesn't really, you don't actually need to allocate that many. So get pass attribute count, just return get output count. Easy as that. Now data list pointer, you want to get pass buffers in the shader program, and you just return the pass buffers. So now there's another function that we need to add, execute fragment shader, which takes in just a data list pointer, pass attributes, and a vector for the output, a vector for reference for the output. And this is just going to return fs.execute, and we pass in the pass attributes in the output. So it's just a wrapper. In the fragment shader.h, we need to implement this execute function. So return a bool and data list pointer at pass attributes and a vector for reference output. Now in this, we can just do a placeholder, return hashtag or something. And let's make sure that's a char actually. And also go to basic shader.h. Actually, let's go into shader program.h and have that return a char. So that should clear up all the errors. So now data list pointer back in raster.cpp equals get pass attributes. And let's go ahead and define pass attribute v1 as 0, pass attribute v2 as 1, and v3 as pass attribute out as 3. Oh, and we're using, make sure that says get pass buffers, not get pass buffers count. Okay, so we need to make some changes to data list. We need to do a get total. This is just the number of actual variables that are stored in the list. So indices index, this will get the total number of variable values in the list. And then you do get raw value, which will use a random index, so it's not based on an indice in the list. It's just a raw index. So set raw value takes in a raw index and sets it equal to value. Finally, we just need a clear function, which just sets index to 0 and indices index to 0. We don't actually need to clear the data, just reset the pointers. So pass attributes sub pass in attribute v1 dot clear, and we just need to clear each and every one of these attribute lists. Once those are clear, we're free to pass them to the vertex shaders to do their to actually add attributes to them. So in the vertex shader execute function, we need to pass in a data list pointer attributes out, and then we need to pass that in from here. Okay, so now we're going to go in and comment all of these out for now and get rid of the vertex shader function, because I'm just going to implement this without that function. So we'll just call shader.execute. Remember, this is doing the same thing. We're just removing the wrapper function for speed purposes. It'll most likely be optimized out anyway, but just to be sure, we don't need the wrapper function. So we just need to change all these to v2 and v3, and then 1 and 2. And then, of course, vertex 2 and 3 there. So the vertex shaders will essentially be writing to those output buffers. So now let's do v1.x divided equals v1.z, and of course v1.y. And do this for v2 and v3 as well. Once that's added, we can go ahead and do pass attributes sub pass attributes v1, and we're going to call clear here, because we just need to clear each of them at the end of the frame as well. Okay, so now that that's added, we're actually good to go. So let's head up into our rasterize triangle function. And this is where we're actually rasterizing the triangle. We need to do that with the fragment shader instead. So the output variable needs to be changed based on the fragment shader. So in the bind function in the data list, let's change something. If values are equal to null pointer or not equal to null pointer, then you copy them. But if they are equal to null pointer, then we can just increment the index by count. And that's going to allow us to just allocate space rather than actually copy data to it, which would be slow. So the raw size is the value we need here, and we're just going to essentially allocate the pass space. So we're going to loop through, we're going to allocate space in the pass buffer. So we just loop through the first one. All these should be the same. The pass attribute v1, get total count, and then you do pass attributes sub attribute 1 or attribute out dot bind null pointer, and give it the pass attribute sub 1 attribute 1, and then get the size at that index I, get location size of I. So that'll essentially, at the end of this entire loop, we're gonna have allocated space, the correct amount of space inside of the output buffer, and created a raw size variable. So we do have to do this every frame, but because the pass variables could change from frame to frame, but it shouldn't be too slow. So now we need a float z1, and this is our barycentric interpolation that we went over in the precursor video. But you cannot do raw barycentric interpolation because you cannot do the interpolation in a fine space. To summarize it, you need to interpolate between the inverse z values. So let's create a function, get barycentric coordinates, pass in the int ptx, pty, and the vector 2 reference v1, and of course v2 and v3. And this function is designed to just give us our barycentric coordinates and not calculate whether it's in the triangle or not. So we'll pass in a vector 3 reference for the output coordinates. Now we can use the code from our isPoint and triangle function, because we actually used that to calculate the barycentric coordinates before, which is wv1, wv2, etc. So if we just set chords.x is equal to that, chords.y is equal to this, and finally chords.z is equal to this. Actually, chords.z is equal to chords.x, 1 minus chords.x minus chords.y. So now is point and triangle can just take in a vector 3 reference barycentric coordinates. Make sure it's const because we don't need to change that. So instead of using WV1, we just use barycentric coordinates.x and barycentric coordinates.y and of course barycentric coordinates.z. And that will be the replacement for our current is triangle and function calculation, or is point and triangle calculation. So down here, vector 4 or vector 3 barycentric coordinates, and then we can call get barycentric coordinates with this. Give it ij, v1, 2, 3, same as usual, but instead give it the barycentric coordinates. Now we can pass in those barycentric coordinates to the is point and triangle function. If we build this, it'll work exactly as before. Nothing's changed so far. But is point and triangle, we need to create the interpolated inverse z value. And that's just going to be z1 multiplied by barycentric coordinates.x plus z2 times barycentric.y plus z3 times barycentric.z. Basic barycentric interpolation, and we did go over that in the precursor as well. So we're going to loop through every value of the pass buffer with I equals 0, I is less than our raw size, I plus plus, and we can interpolate between each raw value. We don't need to worry about anything else. So value 1 is equal to the pass attribute sub 1, and we do this for each of them. And we do get raw value I. And you divide this by the barycentric coordinate, or not the barycentric coordinate, you divide it by the z value. Because you're interpolating between the values divided by z, and then you multiply it by the interpolated inverse z. And then you have the float interpolated value is equal to the value times barycentrics.x. Once again, linear interpolation across the triangle, value 2 times barycentric.y plus value 3 times barycentric.z. Easy as that. You get the interpolated value. And now to pass into the pass attributes, you do the pass attribute out, and then you do set raw value. And then you give it the index and the interpolated value divided by the interpolated inverse z. And that will be the interpolated value taking into account the z divide. So the output character is equal to the shader.execute fragment shader, give it the pass attribute, we give it the output one, and the vector 4, we just need to create this. Right now it's not used for anything, but it will eventually be used for something, or could eventually be used for something. And we give it the fragment out. Go ahead and give it the output char instead. Oh, we do need to make sure that that's a character, not a float. And then also end the line with a semicolon. And if we build, this should work. You notice it's outputting a period now. So if we go into the basic shader, the fragment shader one, we can change this to whatever we want, slash whatever. And if we build this, we'll see that it's executing with all slashes. Now what's cool about the shader is you can specify any character you want to output here. Yeah, we had to save it, but it works. We can specify any character you want. So you can do random modulus like z minus a plus a, and that'll give a random alphabet character. But what's nifty about this is you can actually use it to do calculations and calculate the character. Alright, so now that's out of the way, I hope you learned from this video. In the next tutorial we're going to do actual lighting, as you can see on screen, which is just simply taking the shader program and doing math to calculate the output rather than a random value. So I hope to see you there.